Hello everyone, my name is Biao Kwang. I'm a PhD student at the University of Utah. Today, I will share our CITES-funded project on artificial intelligence and mobile phone-based transportation asset management. This project focuses on two major roadway maintenance issues: pavement marking condition assessment and roadway litter identification. Pavement markings are critical transportation assets because they provide roadway guidance, warnings, and information for drivers and pedestrians. However, pavement markings are easy to deteriorate due to traffic wear, weather exposure, and slow operation. As shown in these examples, many markings become faded and difficult to recognize. These deteriorated markings can reduce visibility and increase safety concerns. Therefore, pavement markings require frequent inspection and timely maintenance. In addition to pavement marking deterioration, another important roadway maintenance challenge is roadway litter debris. Examples include vehicle debris, plastics, leaves, and roadside waste. These materials not only affect roadway cleanliness, but also obstruct drainage systems and introduce traffic safety concerns. According to previous reports, roadway debris contribute to over 50,000 crashes in the United States between 2011 to 2014. As a result, transportation agencies require frequent roadway inspections to identify and remove this issue efficiently. Currently, roadway inspections rely on manual efforts or specialized inspection equipment. Manual inspection processes are often labor-intensive, time-consuming, and subjective. Specialized inspection devices, for example, the retroreflectometer, can provide accurate measurement, but they are expensive and difficult to apply in a larger scale. As a result, traditional inspection approaches are not ideal for scalable and frequent roadway inspection. This created a strong need for more automated and cost-effective way to inspect transportation assets. One promising solution is the application of artificial intelligence. AI models can automatically detect and classify roadway issues directly from images and videos with high accuracy and near real-time performance. Previous work has successfully applied AI to pavement distress detection, traffic sign identification, and pavement marking evaluation. Our previous MPC-funded project successfully demonstrated the capability of AI in detecting objects using mobile phone-based video data. The previous work focuses on object identification. It aims to answer the question, what's the object? For example, the framework could identify whether the object is a faded pavement marking or roadside litter. However, practical transportation asset management requires more than simply identify roadway issues. Transportation agencies also need to know how many issues exist within roadway sections, whether the issues are located, and how the inspection results can be visualized and interpreted. Therefore, important gaps remain in this field. In this project, we aim to extend our previous work by developing a more comprehensive and scalable roadway inspection framework. Specifically, this study focuses on 5 major objectives. First, expanding roadway inspection datasets. Second, improving object detection performance. Third, developing object counting capability. Fourth, estimating the geolocation of identified objects. And finally, building an interactive visualization interface for transportation asset management. This slide presents the workflow of the developed framework. First, we use a mobile phone to collect the videos and GPS data. The collected videos are converted into image frames and manually labeled for AI model training. Next, YOLO 8-based detection models are trained to identify pavement markings and roadside litter. Then tracking algorithms are used for counting unique roadway issues. Afterwards, GPS data and interpolation methods are used to estimate the geolocation of identified object. Finally, the output, including probed imagery, object class, inspection information, and geolocations, are integrated into an interactive visualization interface. Overall, the framework combines detection, counting, geolocation, and visualization into a unified transportation asset inspection workflow. First, for data collection. A mobile phone was mounted on the windshield of a car to record roadway videos when driving. At the same time, GPS data are also collected using a mobile phone-based GPS tracker. The videos are recorded across highways and local streets in Utah. Different lighting and weather conditions are included to improve model robustness. After collecting this data, we use a spatial tool to label these images for pavement marking and litter separately. For pavement marking issues, we develop a dataset including around 7,000 label images. The pavement marking issues are classified into two categories: white-faded markings and yellow-faded markings. White-faded markings include all line markings, arrow markings, and word markings in white. Yellow markings are the faded double and single curve or line markings in yellow. For roadside litter detection, we develop another large dataset. Roadside litter is classified into four categories: leaves, dirt, white litter, and black litter. White litter is a litter in white or bright color. Black litter is a litter in black or dark color. We also consider the dirt along the concrete guardrails and leaves on the roadside. For detection tasks, the study adopts YOLO V8 as the key object detection architecture. YOLO is a single-stage object detection framework that performs localization and classification at the same time. Therefore, this model has high computational efficiency and can be used for near real-time roadway inspection. Using the labeled dataset, we train separate models for pavement marking issues and roadside litter detection. This slide presents the metrics used to evaluate the performance of the trained detection models. We select precision to evaluate the reliability in classifying objects as positive, and recall rate to assess the model's capability to detect positive objects. We also select everyone scores to evaluate the performance. For pavement marking issues, the model achieved strong detection performance with an average detection rate of 0.88, recall rate of 0.89, and everyone score of 0.88. This slide has demonstrated some examples of identified pavement marking issues. We can see that the model successfully identified different types of faded marking, including faded white line marking, word marking, and some line markings in yellow. Our model also has decent performance in detecting roadway litter and trash. It achieves an average precision of 0.86, recall rate of 0.82, and everyone score of 0.84. This slide shows an example of litter and trash identification. It also has good performance in identifying black litter, white litter, leaves, and dirt. Object detection alone is insufficient for transportation asset management. Here's an example showing the detection result across different video frames. We can see the same object appears in multiple frames, which causes overcounting. However, in practice, counting is helpful for maintenance planning. It's better to know how many detected objects in your videos or road sections, so that the transportation agencies can plan their maintenance work. This study adopts backtrack as a key object tracking algorithm. By applying backtrack, objects are assigned unique ID in a sequence of video frames. By spatial similarity, and appearance similarity. Tracking links the detected object across frames. In this way, the counting models reduce duplicated detection and allows reliable counting of unique roadway issues. Next, I will present a case study showing the counting results. This case study was conducted using around 35 minutes of highway videos data collected in Utah. In this case studies will show how pavement marking issues and later are counted along with the detection. In this demo videos, we show how we count the object. We can see when the object is detected, the counting number will increase as well. Finally, in the case study, there are around 500 weight-faded markings in this test road section. Then in this demo videos, we show the result of counting identified litter and trash on the roadway. We can see the count number on the top left increases when the object is detected. In this case studies, there are 33 white litter, 263 black litter, and 102 dirt on the roadway. That's detected in the case study for section. After counting roadway issues, the next step is to determine where these issues are located. Accurate geolocation is essential for practice maintenance planning. Transport agencies not only need to identify roadway issues, but also need to know their locations to prioritize maintenance work. In these sessions, we aim to answer the question, where are these detected objects? Let's review what we have done so far. We have used a mobile phone to collect videos, which are 30 frames per second. Based on detection and counting model, we can obtain the timestamps of each detected object. Meanwhile, we use a phone-based GPS tracker to record GPS information. It records 2 times per second. We can see the timestamp of GPS record that match the timestamp of detected object. Therefore, detected object is not able to fully match with GPS record. Here we proposed a time-based interpolation to estimate the latitude and longitude of detected object. In this way, the geolocation of detected object can be estimated. To evaluate the geolocation performance, we conducted validation using around 3,500 GPS records. Among these records, 135 record points are randomly selected as ground truths, and the remaining points are used to estimate this point. Next, we compare the estimated locations with their ground truths. Finally, it achieves an average distance error of only 0.27 meters, which is a good performance. Based on the proposed framework, we have located the identified object in the case studies for faded pavement markings and litter. Each identified object is marked using a marker. If we click each marker, we can see some inspection details, which are the visualization interface we designed. For example, for pavement marking, if we click each marker, we will see a pop-up window. The pop-up window includes many details of identified pavement marking issues, such as geolocation, the latitude and longitude of the marking issues, the type of object, its weighted feet marking, inspection information including time and driving speed at that time. It also includes the largest crop image of the object, which shows how it looks like. The same with the results to visualize litter detection. This visualization is very helpful for planning maintenance work. It can be used to map pavement marking issues, visualize litter distribution based on which transportation agencies can identify maintenance or sport areas to plan fixed work. To summarize, this project has extended our previous work by developing an end-to-end AI inspection framework. It includes object detection, counting, geolocation, and visualization. For object detection, it can detect different objects, including pavement marking issues, litter, and trash. For object counting, our work can quantify the number of identified objects within a road sections or video clip. We also extend the capability of the model to estimate the location, including the latitude and longitude of each identified object. We finally develop a visualization interface to represent the details of each identified object on an interactive map. For the practical contribution, this study develops an integrated AI-based transportation asset inspection framework. This is a low-cost and deployable approach. It supports proactive and practical inspection and maintenance. It improves roadway cleanliness and safety. It also bridges AI and infrastructure management. Thanks for watching. If you have any questions, please reach out to us by emails. Thank you.